your final projects. Again, your final project is your final exam. So yeah, make sure to do a good job, do amazing things, be ambitious, swing for the fences. It's okay if you fail. I'd love to see you try some really interesting things. And I'd rather see you try a really interesting hypothesis and fail than choose a safe problem and succeed. So yeah, without further ado, then we will get into deep residual networks. So as far as importance of deep learning advancements of the last decade or 15 years, I would put this idea of residual networks up there with AlexNet, who was the one who got neural network training working on GPUs and training extremely fast. Yeah, deep residual networks basically unlock more than like 15 layers, and we're going to see that today. And yeah, so I guess we'll just jump in rather than try to preview it. We'll just go right into this. And then also credit to Kai-Ming He, who is the inventor of residual networks, or ResNets, for all of these slides. So you're hearing it, if not from the horse's mouth, at least from the horse's slides. Okay, so deep residual networks. Basically, this is one simple trick that doctors hate. Actually, no, that deep learning practitioners love, which allows you to train much deeper neural networks. And the trick is adding skip connections. So you've seen skip connections before. You've seen them in transformers. You've seen them in the UNet architecture. But here we're going to look at why they work and yeah, some important nuances to the reasons why they work and the conditions under which they work. So by way of results in this COCO class image computer vision challenge in 2015, ResNets basically blew away the competition. So they were able to train a network with 152 layers, whereas previously people struggled to train networks deeper than about 30. And yeah, on ImageNet detection, they got a 16% error rate, or they were 16% better than second place. ImageNet 27% better, COCO 11% better, etc. So it's a pretty significant jump in accuracy on these image classification on these computer vision networks. So yeah, this is a comparison of the error rates on ImageNet classification across 6 years of this competition. 2012, you can see we had a huge drop from in 10 absolute % error points when we introduced GPU training and slightly deeper networks, 8-layer convolutional neural networks. That's AlexNet. And then we can see that as people started to adopt those similar techniques, they continue to decrease error. But then as far as like order of magnitude, the improvement from 2014 to 2015 was only 3 absolute percentage points, but that's a 50%. But that's a 50% improvement in error rate of 6.7 compared to 3.5. So really, like the difference in bars is not that big, but in like percent change, it's pretty significant. And again, you can see we were able to go from 22 layers to 152 layers, and that's the main reason why ResNet was able to do so well. So yeah, this is architecture of AlexNet, 8 layers. This is next to it, we have VGG, 19 layers, GoogleNet, 22 layers, and then 2015 ResNet, just give you a little picture for scale. Okay, let me double check to make sure I'm recording. Yes, we are recording. Okay. Yeah, this is another example of an object detection challenge, and again, seeing significant jump in accuracy with deeper nets, which are enabled by residual connections. So this is just an example of what it's able to do. So this is an object detection class. I'm not sure we've looked at object detection in this class before, but basically the challenge is, given an image, draw a bounding box and around different objects in an image and classify what is in that bounding box. And so there are several different ways to do it, but a common technique is to choose a center point and then choose a height and width going out from that center point. And then also, so you would regress, you would predict 4 values, basically associated with the x and y of the center point, and then the height and width emanating from that center point. So that you would do regression on the coordinates of the object detection box, and then classification on the class that falls within that box. And you can see it's doing pretty well. It looks like we have maybe some sort of family gathering. Oh, it's a birthday. Kind of looked like a stack of textbooks to me. My object detection isn't very good. Oh, and look, it got fooled as well. It also thought that was a textbook instead of a birthday cake. But yeah, so we have a birthday cake getting classified as a book, but oh, looks like it also classified this as a cake. We have a wine glass, knife, dining room table, person. So it's doing pretty well. Yeah, getting fooled on some things, but also I got fooled on some things. So, okay. Yeah, so basically, so if you look up the ResNet paper, I'm pretty sure it has at least 5,000 citations, maybe more like 10 or 15,000 at this point. Okay. Yeah, so this is kind of a guide of how we go from shallow networks to deep networks. So normal backpropagation and gradient descent seems to work pretty well with networks up to about 5 layers. Once we started to see deeper networks, we saw at the beginning of this class that those the ability to train those networks depended heavily upon the initialization of those networks. And also, we saw that batch normalization was a pretty effective technique to prevent vanishing gradients as well. But yeah, once you start getting up to about 30 layers, you start running into those issues again. And so these techniques of initialization and batch norm can only get you so far as depth. But with ResNet, we can jump from 10 to 30 layers, and that's by introducing these skip connections. And we can go all the way up to 100 layers by introducing what we will call identity skip connections. So something that we'll see today is that not all skip connections are created equal. And then question is, can we go even deeper to networks of 1,000 layers or more? Okay, so actually just a question. Why do you think more layers are better in a neural network? Why might they be better? Yeah, Spencer?
Going back to the handwriting example, the first layer was picking out lines, and then the second one's like starting to move them around, and then it kind of combines them. And so they're all picking up pieces that then layers can either recombine or find extra aspects of that then allows it to make connections. So the more layers you have, the more patterns it can recognize, and thus make more complicated predictions instead of just, instead of just accumulating data and then processing it a little bit and spitting something out, it can actually think about what it's been given.
Yeah, I think that's a great explanation. Yeah, Dane, you want to give it a shot?
Sure. I kind of think about neural networks almost like an analog to writing a large program for a particular problem you're solving. And generally, when you have more code with purpose, it can cover a broader spectrum of functionality. So I think that sort of maps over nicely to the idea of more layers, more code, kind of similar concepts, although they're different in how they're architected.
Yeah, interesting. Yeah, I like to think of it as the deeper you go, the more abstract features you can learn, the more you can combine and recombine features, kind of like Spencer was saying. And we can learn these very deep, complex representations of our input. Yeah, so but we see some interesting things when we start to try to train these deeper networks. So with a 22-layer ReLU-net, here we have, I forget what it's called. I believe that red is he initialization and versus blue is Xavier, perhaps. And we can see that with better initialization, we get faster conversions. Once we go up to 30 layers deep, the difference in initialization is the difference between learning nothing at all and converging. So yeah, with shallower nets, we see that good initialization helps, but with deeper nets, it makes all the difference. As a reminder, so batch norm is normalizing each layer for each mini batch. So this is to make sure that the network is always receiving inputs of similar magnitude at each layer. And so to do that, we will normalize all of the features across each mini batch. And then the other part of that is, so the first step of batch normalization is you make your mini batch centered at mean 0 and variance 1. And then we also learn a new scale and shift in gamma and beta. So we take our centered normalized input and then we scale it according to a decision that the network will make by choosing those parameters gamma and beta. Any questions on that little batch norm review? Okay. Yeah, and then also a reminder that the batch norm works different in train mode versus in test mode. So in train mode, mu and sigma are functions of our mini batch. And in test mode, we just use the mu and sigma for our entire training data set and apply that to our inputs because we don't want our normalization to rely on having other test points. Okay, so this is just a view of the effective batch norm. The baseline is the inception network without batch norm, and then these other curves are introducing batch norm and also going deeper because the last one is batch norm with 30 layers because batch norm allows us to train deeper networks. Okay, but then how do we get past this seeming barrier at 15 to 20 layers? So can we just stack more layers if we have good initialization and good batch normalization? Well, let's look. So if we try to do that, this is the result. So we have a 20-layer network in yellow and a 56-layer network in red, and we can see that, and on the y-axis is error, and we can see that even in the training data set, the 56-layer network is not able to do as well as the 20-layer network. And then similarly at test time, the 56-layer network is not able to converge as well as the 20-layer network. Okay, and then this is another example of something similar where, again, we see a monotonic increase in error as we increase the number of layers. So this isn't just a fluke going from 20 to 56 layers. This is a pretty consistent trend that we're seeing. So, but this, if you think about it, this really shouldn't be the case. And this is an argument that he makes in his paper is we can, by construction, create a deeper network that is fully as capable as the shallow network. The way we do that is we are just going to take the shallow network, space out its layers, and insert new convolutional layers, but initialize them to the identity. So initialize these layers to do nothing to the input and just pass it through. And so theoretically, we can find a solution for a deeper network that is exactly as good as the shallow network. Yeah, Dane, you have a question?
Thanks. If we can do better with a shallower network, why would we be drawn towards a deeper network? Seems like more work, more memory. What's the gains in accommodating a deeper structure?
Yeah, great question. I mean, I would say that the first thing is empirically, we see the improvement going from 5 layers to 20 layers, but then we see performance start to cap out at 20 layers. And so the thought is perhaps, and that also and that empirical observation that deeper is better matches our intuition that deeper networks let us learn these deeper hierarchies, more complex features. And so the idea is that we think that deeper networks are better, but there's just some sort of computational difficulty or difficulty in optimization that's preventing that from happening. Yeah, good question. Okay, so any questions on how we can create a deep network that is equivalent to a shallow network? Okay, so yeah, the idea is that we have a richer solution space. Then if we take this equivalent deep network and initialize it with the weights of the shallow network, it will have exactly the same loss, and hopefully we'll be able to learn something better than that loss by optimizing those remaining weights. So this is how we're going to try to do this. We're going to take our input to a set of 2 weight layers. These could be convolutional layers, they could be fully connected layers. And we are going to simply add the input to those layers to the output of those layers. And so if you think about it, this is kind of based on the intuition of that deeper network that we created by construction, right? We allow the network to basically learn a smaller network by providing these identity skip connections. Does it make sense, the relationship between adding this identity skip connection and our deeper network by construction? Does someone want to take a shot at explaining that back to me, the connection between those 2 things?
Well, you initialize the weight layers to 0, and instead, when you add the identity to it, it's as if the weight layers were initialized as identity matrices. So that then when it is looking for the gradient to put back through the weight layers, it will treat them with loss, even though their weights are initialized to 0.
Exactly. Okay, so based on this intuition of constructing a deeper network with identity paths, we're going to introduce this identity skip connection that's just adding the input to the output. And so this is the design of the network. And actually, there's kind of a funny story behind this. So Kaiming, he had this idea and just spun off an experiment over the weekend. Just had I'm pretty sure he might have been using the VGG network and just made it deeper and added this little skip connection to all of the layers and just set it off to train over the weekend. And he came back and he had state-of-the-art results on ImageNet. So kind of a fun, the dream of what you would hope would happen with all of the experiments that you set off over the weekend. So if you're ever thinking of going home, but you have the opportunity to occupy your GPUs over the weekend, just try something. Like, if you have an idea, just try something, set it off to run, and maybe you'll revolutionize deep learning. Okay. So yeah, and then in their experiments, all of them use batch normalization. All of them use good initialization strategies, and the only difference is adding these residual connections. So take a look at this slide and tell me what you notice. We saw a very similar slide earlier. What do you notice is different about this slide?
This time the deeper layers are getting more accuracy than the shallower networks.
Yeah, exactly. So just with this one small trick, we go from deeper layers hurting accuracy to deeper to more layers, increasing accuracy by quite a bit. And that's on both test and train. So the solid lanes, the dashed lines are train, and then the solid lines are test. Okay, so yeah, again, some more experiments. We see before residual connections, a 34-layer network has higher error than an 18-layer network, and adding residual connections flips those. Okay, so yeah, they decided to do some experiments on variations of this skip connection. So yeah, so first of all, they experimented with the type of convolutions in between. So here we have two 3x3 convolutions, and then on the right we have 1x1 convolutions sandwiching a single 3x3 convolution. And yeah, basically, so they were using this new technique. They were able to basically get higher accuracy for similar computational complexity as the two 3x3 layers. And so as a result, these ResNets, even despite being deeper, and Dane was pointing this out, they're probably also computationally more expensive. They were able to, by combining residual connections with some experimenting with the layers in between those connections, they were able to achieve lower time complexity than a 16-layer network with a 152-layer network, while achieving much better error. Okay, and we already saw those results. Okay, so these are their these are kind of some constraints of training deep learning models, just practically, and some claims about residual connections. So can I get someone to read the representation ability? Yeah, Jaden.
Ability of model to fit training data if optimum could be found. If model A's solution space is a superset of B's, A should be better.
In your own words.
Oh, I have to actually read it this time. So the first part of it, like, it's just its ability to like truly, actually get the training data, right?
So you always have access to the training data. It's more a question of whether your model has the capacity to learn your data set. So for example, we would expect neural networks probably to have more representational capacity than maybe a shallow decision tree. And we would expect deeper neural networks to have more representational capacity than shallower networks because they have more parameters and can learn a deeper hierarchy. Does that make sense on representation ability? So yeah, first bottleneck is model capacity. Second one, someone want to take a shot at reading the second one and rephrasing it their own words? Hey, Drake.
Feasibility of finding an optimum, and not all models are equally easy to optimize. I guess that just means like whether they converge or not to the solution.
Yeah, exactly. And so we found that networks that use batch norm and use good initialization are easier to optimize than networks that do not use those techniques. Yeah, and then generalization ability.
Well, it literally says, once training data is fit, how good is the test performance? So I think it's just talking about you have challenges in making sure that your model represents the problem you're trying to fit.
Yeah, great. Can you maybe think of, in the context of this class, two training schemes or maybe two loss functions that would one which could be expected to have better generalization versus one that would be expected to have worse generalization? Any thoughts? How do we normally try to improve generalization of neural networks? Regularization, great. Yeah, what are some techniques for regularizing neural networks? Shout them out. Dropout. Shakeout, what? L2 normalization, weight decay, yeah. So yeah, and so yeah, to sum up kind of what we have here is yeah, previous to ResNets, representation ability, we usually want to go deeper. Optimization ability, we want to use batch norm and initialization, and generalization ability, we want to have some sort of regularization, whether that's dropout or weight decay. Okay, so how do ResNets address these? We don't have an explicit advantage on representation necessarily. We could theoretically make deeper networks, but they're just super hard to optimize. And so we're able to make deeper networks, so we improve representation ability. And so this one, so really what they offer is optimizability. So it's much easier to optimize ResNets, which allows us to make deeper ResNets. And then also, this one is an interesting claim that I'm not sure I'm convinced of. This isn't one that they showed in the paper, but they claim that deeper and thinner models offer better generalization than shallow, wide models. Do you know what I mean by deeper and thinner versus shallow and wide? So deeper and thinner, I mean more layers, but fewer hidden or fewer nodes per layer, versus shallow and wide would be only like 3 layers, but each layer is like 1,000 by 1,000, and so your activation maps are much larger. Okay. All right, so these are some experiments that show how important it is that our skip connection takes the form of an identity mapping. So yeah, we've already seen this. So actually, no, this is a little bit different. So before we were doing, so actually, sorry, this is a diagram of the most general case. So we have a layer in between. We have two layers. We're not going to say what kind of layers those are yet. We have some function of the input, h of xl, which maybe it will be the identity, maybe it will be something else. And then we also have f, which is a function applied to the sum of the identity mapping and the neural network portion. And so we're going to experiment with different value or different functions for h. So different identity map, different modifications of the input. And we're also going to experiment with different versions of lowercase f, which is the function applied to the sum of the residual and the output. So yeah, the first thing we're going to look at is what if we do not, so before we were looking at applying a ReLU after this sum. Now we're going to look at not applying any activation after that sum, and also not applying any function to XL. So basically what this leads to is a very smooth, what he's going to call smooth in a very non-rigorous sense, forward propagation. Basically, we're going to have no composition of functions between XL. So we have XL, XL plus 1, and XL plus 2. These are the outputs at each layer. And if we were to have something other than the identity for H and for lowercase f, then what we would see kind of a nest of functions around XL. But instead, if we use the identity for both of those, XL plus 2 is directly a function of XL, as well as a function of a transformation of XL and a transformation of XL plus 1. Does that make sense? How by using identities, L plus 2 is directly a function of XL? Okay. And then to generalize this, if we go to the end of the network, the last activation of our network is still directly a function of XL, which is the first input to our network. Yeah, and so this is just restating the same thing. XL is directly a sum of the outputs of all the previous layers. X capital L versus if we were to leave out these skip connections, X capital L would be basically this nested, this deeply nested transformation of XL. So WYXL followed by a ReLU, followed by multiplication by another weight matrix, followed by a ReLU. And so a much less direct path between X capital L and X lowercase l. And the result of this is that we also, and this is probably the key. So if I was being a little too boring, you can start paying attention again now, because this is really important. So because we have a direct path between X capital L and X lowercase l in the forward pass, we have a very direct path between our loss function and X lowercase l in the backward pass. If you remember, this is hearkening back to the beginning of the course, when we computed our gradients with respect to the earliest layers of the network, we were using a chain rule of probability with like as many as 50 terms, right? But if we have skip connections, then our chain rule of our loss, which is directly a function of X capital L, is only one partial derivative away from x lowercase l. And we could also think of this as really what we should think about is w lowercase l, because we care about optimizing our weight matrices. And so, yeah, the derivative of our error with respect to a given weight matrix, x lowercase l, is just the derivative of the error with respect to the last output of our network times the derivative of the last output of our network with respect to that weight matrix, which is just 1. And so, well, it'll be 1 plus these other partial derivatives. But the point is that we have a very direct way to modify each weight matrix by our error. Yeah, question, Drake?
A huge chain rule idea though, just because we're still running a lot of weight matrices.
Great. Yes. So great question. So when we still have that huge chain rule, and the answer is yes. So that huge chain rule is this derivative with respect to x lowercase l of this big ugly nested function. But the important part is that we do have a term in here that is 1. And so you can modify XL using that big, ugly chain rule of derivatives, but we can also modify XL directly with that derivative that's just 1. Does that make sense? Okay. All right. Yeah, so again, this is reiterating a lot of the same points that we've been talking about. So, and yeah, to review our why this is possible, it's because we let H be our identity and also our lowercase f be the identity. So to make sure though that this is actually what's happening, they ran some experiments. And so they tried changing H and changing f. And these were the results. So what if we make the shortcut mapping something other than the identity? So this is kind of confusing. On the right-hand side, we have the network, and on the left-hand side, we have the shortcut. So the first one, top left, is just the identity, and we get error of 6.6%. Top right is we're just going to apply a constant scaling, and that immediately bumps our error from 6.6% to 12.4%. Then they tried some other kind of more interesting things like a gating function that gives you the option of incorporating additional information in this identity path. Not applying an identity at all, but instead applying a different convolution, applying dropout instead of an identity. And you can see what is the effect of doing anything to the identity? Increases our error, which is a bad thing. I don't know why all of these are in green except the best error. I would probably change those so that the error of 6.6 was green and all of the other ones were red. But yeah, so basically anything other than the identity, we're losing error, which matches with our intuition of how important that direct path between our error and the weight matrices is. Yeah, Max.
So I was just curious, it looked like in the other network, there was like these skip connections that were dotted lines. Are those so that we still have ReLU layers so that we maintain being able to learn nonlinearity in the data, or are there no ReLU or any activation functions anymore?
So the ReLU, there is no ReLU in the identity path. So the ReLU has to do with lowercase f, which we're going to look at actually right now. Yeah, so yeah, I'll answer your question before we move on. So there are two different things. One is there were some dash connections in the original ResNet, and that had to do with shape compatibility. But as far as ReLU, yeah, the short answer is you don't even want ReLU on that identity path, which is kind of interesting. Like the identity path is linear, it's not nonlinear. And so you don't, the entire network doesn't need to be nonlinear. You can have a nonlinear part of the network that it's able to use while maintaining a linear identity path. Well, yeah, so there's a ReLU, there is ReLU. If you look on the right-hand side of each of these diagrams, there's a ReLU in between the 3x3 convolutions. And so there is a nonlinear path, but not on the identity. Okay, so yeah, again, we're seeing that in 5 of these instances, we have shortcuts blocked by multiplications. And we can see the effect of this mathematically when we compare to our original chain rule. If we have a multiplicative shortcut by a factor of lambda, x sub capital L then becomes equal to lambda to the L minus 1 times XL, which means basically that the direct propagation of XL is decayed exponentially to the point where it's barely even visible by the time you get to the error. So that should make sense. Kind of why that multiplicative shortcut kind of blocks the signal between the loss and x lowercase l. Any questions on the exponential decay due to the multiplicative shortcut? Okay. Yeah, so the gating option is kind of interesting because these still allow the possibility, the gating option still allows the possibility of learning an identity because the identity is a special case of the gating function. But it turns out to be hard to optimize. And I would also argue that like, technically a convolution can also learn an identity. And so convolution technically should be better than this as well. But again, we're seeing we're seeing problems anytime we interfere with that direct identity path. Okay, so this is what we were talking about with Max. What happens if we have a nonlinearity between after adding our skip connection? So we have 3 different experiments. A pure identity on the right, batch norm plus ReLU in the middle, and then a ReLU on the left. And we can see that anytime we add complexity, where our error is increasing. So yeah, identity is better than ReLU, and ReLU is better than batch norm plus ReLU. Okay, and just more results showing that ResNets and identity paths are the best. Okay, yeah, so to summarize, the goal is to keep the identity path, or the path between our loss and each of our weight matrices as short as possible, and specifically the gradient path. And we do that by making both H and F identity functions. And yeah, that's about it. Any questions on ResNets before we conclude for today? Yeah, Jaden.
Guys, first one. Identity connection and skip connection.
Good question. Yeah, so the difference between an identity and a skip connection. So the skip connection is the general case where we have some H of X and some F of X that are not necessarily the identity. So we had a skip connection that used a gating function. It's still a skip connection because there's basically a skip connection is anywhere there's a forking path that comes back together. So different transformations are happening on each sides of that path. That's the definition of a skip connection. And so we saw skip connections with gating functions, with scaling functions, et cetera. But we found that the identity was the best skip connection. Yep, an identity is a type of skip connection. It's the simplest type and also the one that works the best. Good question.
The second question was, does style transfer still work with a ResNet?
Question is, does style transfer still work with the ResNet? Absolutely. So it turns out that like the networks, the identity connection does not hurt the ability of the network at all to learn features in its other layers. And so, yeah, same like feature extraction, representation learning still works.
Does it ever help to add like skip connections between multiple layers, like if just one layer?
Great question. So the question is, rather than having a skip connection basically linearly through the network, what if you increase the number of skip connections? The answer is yes, it's called DenseNet, and it works even better than ResNet. Yeah, good question. All right. Thanks for coming. See you on Friday.